So last time we started talking about obviously solving equilibrium concentrations using ice tables. Remember that the ice table represents initial change and equilibrium. And it's really the change part that we're ultimately solving for. We usually use a letter X is usually used to represent obviously sort of the unknown. We do our sort of initial concentrations, or we could even do pressures as well. And again, if you're just given like the example or a couple of saw, just the reactants amount. So let's just say we had 4 molar of this guy, 4 molar of this guy, but nothing there for C. Again, we would assume that it's starting with 0. And let's put a 2 there. That also means that we can safely assume that this reaction is probably heading towards the product side again, because we have no products to begin with. So we need to make products. So the forward direction definitely will sort of predominate. The change part is the important part. The change part takes into account the mole-to-mole relationship, all the stoichiometry part, and understanding that it is, again, going from reactants to products. We would expect that over time, our reactants should start to decrease as we need to basically use the reactants to make more products. And we do represent that with sort of minuses on the reactant side in this case. We would also look at the coefficients there. And again, if there is a coefficient, we do need to put it in with our x's. And as I said before, that really is the mole-to-mole relationship. So all the stoichiometry will really work out correctly for you as well. And that's when we get, for example, in this here, we get to our product side, it would be positive 2x, again, the 2 because of the coefficient that is there. Positive, again, because we should expect that obviously we should be making products in this case as it heads down towards the product side. We get to the equilibrium, we're just going to simply carry everybody down. And at this point, really, it becomes, frankly, math. So we want to basically solve for x. We would be using our equilibrium expression in this case to do so. This would be like c squared divided by a and b, assuming those are all aqueous. And at this point, we would put both of these guys in. We'll get something like 2x. And we would square it divided by, in this case, 4 minus x times 4 minus x. And probably in this case, we would have been told maybe the equilibrium constant is 70, just making up a number. Obviously, in this case, there's a lot of math we have to do, right? We've got to do some factoring of these guys, got to multiply it to the other side. We also will probably need to, if we were going to solve for this one, use something like we did before, which is that quadratic, right? Where x is equal to b minus b plus or minus the square root of 4ac divided by 2a. And remember, that comes really from the formula that your equation is sort of, you want to get looking like this. Ax squared plus bx plus c equals 0. As I said before, a couple of things about this. Most of the time, x squared usually is kept positive. You don't have to. You can make it and leave it negative if you want, but we usually bring everybody to whichever side will get x squared positive is usually the approach. And also the main important thing, as we talked about, I think towards the end last time, when we do solve for the quadratic here, we will end up with really 2x values, right? And the end result here, as we talked about, could be 2 positive values, could be 2 negative values, could be a positive and a negative value. What's ultimately going to determine, which one you should kind of throw out is really when you go back into the equilibrium line. When you put one of those x values in, it will lead you to a negative concentration, which you can have negative concentration. So that's a really simple way to remember. If you get a negative number for a concentration at the end, not good. You should not have that. Any questions on that stuff we talked about here last time? Now, we did it with concentrations here. You could do the ice table with pressures and use like a Kp value, works the exact same way. This is what I was talking about earlier, that if you are going to do an ice table like this and you are dealing with pressures, they need to be in atmospheres. Yeah. when you go into the ice table. So even if you're given all the pressures in torr or something like that, and they want all the answers in torr, you need to convert it into atmospheres, go into the ice table, do the calculation, and then convert it at the end. So that's an important thing to remember. You'll sometimes come across some problems when they're dealing with pressures. And like I said, they kind of give you the unit, torr or millimeters mercury, and ask for the same unit at the end. So people think logically, I could just use that unit, throw it into the ice table, and I'll get the right answer, and you really won't. So it does definitely need to be in atmospheres if you're going to do an ice table and you're dealing with pressure. Any questions? Yeah. Maybe-ish, but you probably should know 760, by the way, as a conversion, yeah? So 760, you divide millimeters of mercury or torr by, and it'll convert it to atmospheres, yeah? So in case I don't remember, I would remember it, yeah, just in case. Yeah. Other questions? Yeah. 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 Are you asking how you would do the math up here? Oh, this C, I'm sorry, this C. It would be once you basically take this expression here and factor the bottom, multiply to the other side, bring all the terms to one side to set it to equal to 0. Whatever you would get when you do that, the one that doesn't have an X in it would be what C would be. No, C is not the 70 necessarily. You would actually have to, and we're not going to do this, we got some other examples to do, but you basically, before you can do that, you got to do the math here, right? And you'll get like, 4 times 4, right? 4 times X, and then X times 4, X times X. Then you got to multiply that entire thing to the other side. Then you got to combine everybody to one side, all the X squareds and all the X's to one side equal to 0. And at that point, what you should end up with is like usually a number that has an X squared and maybe plus a number that has an X, and then you'll just have a number equal to 0. And that number that's by itself, no X's involved, is what C would typically be. But you actually have to solve it, obviously, to get there. Yeah. Other questions? So why don't we do another one here, and we'll get some practice, I think, on this one here of all fun math. So go for it. Have some fun. I'm going to power nap, but, now I'm going to do it with you on myself on the paper, and we'll see how we do. All right, so take some time here, work this one out. We're starting with 0.5 moles of H2 and 0.5 moles of I2 placed in a 1 liter flask. What is the equilibrium concentrations of everybody? The equilibrium constant in this case is 54.3. So take some time here, and we'll get started in just a bit here and see how you're doing. Again, you should be obviously starting with an ice table. Yes. How you're progressing. So clearly, that's what I just scribbled. So here we do have, obviously, we're looking for equilibrium concentration. So that's just green to ice tables. In this particular case, we're not necessarily given the concentrations, but they're pretty straightforward. We can easily calculate the concentrations of H2 by taking the moles divided by the liters, which in this particular case is dividing by 1, which makes the math pretty easy. That's going to be 0.5 molar for our H2, and it also will be the exact same for our I2. That's going to be 0.5 moles per 1 liter. Going to give us a opening concentration of 0.5 for each of them. Right? We also might want to also write our equilibrium expression here. So our equilibrium expression, K would equal our products, which is HI. We do need to square it because, again, of the coefficient that is there. We then need to divide it by H2 and divide it by I2. And in this particular case, that's going to equal the nice number of 54.3. Any questions so far? Okay. Then we can really get roll into our ice table here. So we got H2 plus I2. I'll ignore their arrows there. 2HI in this case. So initially here, taking the concentrations we just calculated, we should have 0.5 molar, 0.5 molar here. And in this case, nothing was said about our products. So as we talked about, it is safe to assume that it's going to be 0 there initially. Now we get to our change part. We are going to assume, because there's no products, that we should be heading in the forward direction towards the product side. That means our reactant should be decreasing, our product should be increasing. So that should give us a minus x, and a plus 2x. Again, because of the coefficient, meaning that all we simply need to do is carry everything down here. That's going to give us 0.5 minus x, 0.5 minus x, and 2x. Is there any questions on the ICE table there? So at this point, what we want to do is, as we talked about, we now want to take the equilibrium line, basically, and put it into our expression and solve for x. So if we do that, it's going to give us 2x, and we need to square it, divided by 0.5 minus x times 0.5 minus x, and that again equals 54.3 it was, I believe, yeah. Now, when you look at this, you could do some factoring, you could do all that good stuff, or you should always look for perhaps a better way. What would be a better way here? This is a perfect square, yeah? So you could do a square root on both sides, making the math way easier. Put a big square root there and a big square root there, which I always forget to actually square root that number, but you want to actually square root that side. If we square root the left-hand side there, we end up with 2x up on top, and we end up with 1 of the 0.5 minus x. And again, as I seem to sometimes forget to do, actually need to take the square root there on the left-hand side of 54.3, and that's going to give us a 7.36885, taking it to a few digits there. Any questions on that? Now, you absolutely could factor it out and do it that way. Should come out the same when it's all said and done. But, you know, sometimes these problems are a little bit long. So if you can find maybe a shorter way, it might be good. Do you have a question? You can, if you can, in this sense, if it's a perfect square on the other side. Yeah. So the only way we could do it on that side is because we technically get square root the other side. If you can't square root the other side, you can't square root that one. Yeah. So yeah, it's only because we could do it on the left. Other questions? Yeah. Yeah. So basically on the left-hand side, if you think about it, right, let me go back to this page. I write on here. Basically, you have on top 2x times 2x, right? Which is basically 4x squared. And this is basically, if you take the square root, whenever you multiply something by itself, that's squaring it, right? The opposite of that is taking the square root of it. So you're able to do it. And it's the same thing on the bottom there. We basically had 0.5 minus x times 0.5 minus x. That's basically timesing something by itself. Like if you times x would be squaring it. It's basically the same idea. So you can take the square root of it and you'll be left with just 1 of it. So it's really because on the left-hand side, you had that situation as to why you could do it. Yeah. Now, if any of these things were different, like if this guy was like, 0.3, you couldn't do it because obviously it wouldn't be a perfect square. But in this case, it happened to be. Other questions on that? Okay. So it will make the math a little bit easier here if you recognize that. Now what we need to do math-wise is what's on the bottom here, right, needs to be multiplied to the other side. So we're going to multiply everything on the bottom to the other side. I'm just going to go up on top here and go 2x on the left gives me basically 7.36885 times 0.5. Gives me approximately 3.6844. And then we're basically just multiplying x as well to the other side. And I'll go underneath it here, minus 7.36885x. At this point, what we want to do basically is bring all the x's to the same side. Again, you might want to keep x positive in this case. Doesn't really matter, but it kind of just makes it a little bit easier. To do that, we're basically going to add this to the other side, right? That will get it to the other side. And if we do that, we end up with 9.36885x is equal to 3.6884. Again, we're just combining terms, which is commonly what you do in algebra, right? Is you get all the guys together. Anything that's the same sort of value, x or x squared, you put them together. At this point, we're going to solve for x by one more time, taking this guy back to the other side and dividing. So when we do that, we will finally get an x value here of, I believe, 0.393, if I'm not mistaken. Yeah, sounds good. Of 0.393. Any questions on that there? Now, as we talked about before, in this case, we didn't use the quadratic, so we just got one x value, which should be the correct value. That x value, again, is every single x that we see in this table on the equilibrium line. So to finally figure out what is everybody's concentration in equilibrium, we're just going to stick that x in there. So that gives us for H2 a concentration on equilibrium, which is 0.5 minus 0.393. And that's going to get us a 0.107, I believe. And we do need a molarity on that since it is a concentration. I2 is going to be identical, right? So I2 is also going to be 0.5 minus x, which will also give us 0.107. And again, we do need molarity there. And lastly, for the concentration of HI at equilibrium, that is equal to 2 times x. So that would be 2 times 0.393. And that's going to yield us a 0.786, I think. A 0.786 also needs a molarity on it. And these would represent our equilibrium concentrations of each of these. First off, any questions on that there? Yeah. Yeah, so basically, if you took 0.5 molar, whatever the volume that would represent, of each of those guys, and you dumped them into a flask, it would eventually start reacting at the point when it reaches the rate of the forward reaction equals the rate of the reverse reaction. Everybody will lock into place at that point. And where they were locked into place in this example is H2 and I2 will end up at 0.107, less than what it started with, right? And as a result of that, we will make 0.786 molar of our products. That's what that represents. Other questions? We also talked about that. You could check if this was all good. Again, I could check by doing what? Take in each of these values we just calculated, put it into the K value expression, and we should get a number around 54, which you do. I think you get like 53.9. Again, won't be exact, but should definitely be in the ballpark if you do that. Any questions on that? Again, sometimes a more complicated problem, it's a good idea to take the extra second or two and put it back in to the K expression. That's a good way to see if you really screwed up on the math or not, right? So obviously, if you get a K value way different than what you started with your equilibrium concentrations, you screwed up somewhere on the math, right? So it's a good way to kind of check your math. If you're not sure, maybe you messed up along the way. Yeah. 9.36 came from, we had 2x on this side, and we had minus 7.3x on this side. We added it back to the other side to combine the terms, and that's where it came from. Other questions? All right. Let's do another one here. Same equation. But let's go with 2HI here. Got moved around. All right, in this case, we're starting with 0.00623 molar of H2, 0.00414 of I2, and 0.0224 of HI. Equilibrium constant again, 54.3. Go for it. Yes. So we're looking for the equilibrium concentrations here. Okay, let's take a look to see how you're doing. A lot of math in this particular one here, so let's just make sure we're all hitting hopefully the correct steps. In this particular case, we're dealing with the same equation or reaction, and in this particular case, as was mentioned, we actually are given the starting amounts of everybody, which would imply that perhaps this reaction has already started. We're not sure it's at equilibrium. But more importantly, we might want to also figure out which way it needs to go to reach equilibrium. And so this is really another situation where you would actually should calculate Q in this case because you could do it. So this is the place where if you're doing ice tables and you're given the starting amounts of everybody, you really should quickly calculate Q. First, to make sure you're not at equilibrium, which I would assume in this problem you're not, otherwise it's not much of a problem. But more importantly, just to reassure yourself which way the reaction is heading to reach equilibrium. So if you remember, we calculate Q the exact same way as we do K. So we would take HI here and square it. We would divide it by the concentration of H2 and I2. And in this case, we just put the concentrations that were given to us. So we have 0.00623. We're going to square it up on top. And then we got, no, I guess 0.0224 would be a better number there. Sorry. Try again. 0.0224 up on top. There we go. That's the right one. Then we have 0.00623 on the bottom and 0.00414 also there on the bottom. And if we do that here, looks like we end up with a Q value of about 19.5. That means in this case, Q is greater than or less than K. Q is less than K, which first tells us it's not at equilibrium, which you probably could guess it's not. Second, though, it also tells us to reach equilibrium, which way does it need to go? It's to go towards the product side, right? Opposite of where that's pointing. So it actually does need to make products. So that really does help us for sure know that this guy is heading towards the product side. That also helps us understand that we are doing hopefully the minuses and all that kind of stuff correctly when we do it. So this is the other place, as we talked about the other day, where outside of it just a straight Q type problem, this is a place where you could use Q and you really should take Q. I would say even if you blew by this step, probably 9 times out of 10 you'll be okay in most cases, but there are some rare exceptions where it might be going the other direction. Any questions on that so far? Okay, so now we could get into this problem. I don't know if we want to, but we can. Let's try it. All right. So we're going to do our ice table here, and that's going to give us H2 plus I2 going to our 2HI. So initially here for our I, we got our H2, we got 0.00623. For our I2, 0.00414. A little bit bigger, 0.00. I always want to put an extra 0.224. There we go. 0.0224 for our HI. Our change here, just like the previous table, since it's the same reaction, minus x, and plus 2x. Carrying it down in this case, 0.00623 minus x, 0.00414 minus x, and this is 0.0224. Also a place where people kind of make an error sometimes is used to doing minuses, but this is again actually plus 2x, right? So that's actually plus 2x. Any questions on the ice table here? That obviously is going to go into our equilibrium expression, which is the same expression as our Q, which looks like this. So putting that in, we get 0.0224 plus a 2x, and we need to square it, divided by 0.00623 minus x. times 0.00414 minus x. And again, that will equal 54.3. Any questions so far? Now it's like math time, yes? We got to factor out the top guy on the left. It's got to factor out the bottom guy on the left, do some multiplying, all that good stuff. I'm going to do each part separately, and then we'll kind of put it back together there at the end. Might be a good way so it doesn't get all crazy looking. So we will start with the top here. We'll change colors here. All right, so looking at the top, which is this guy here. Come here. That is going to be basically 0.0224 plus 2x times 0.0224 plus 2x. We all know how to factor, yes? In, out, okay. So if we do all that good stuff, you end up with 0.000502 plus 0.0448x plus 0.0448x plus a 4x squared. We could combine the two x terms there, and I'm just going to rewrite it with the x squared first. And for the top, if we do all that, we get 4x squared plus 0.0896x plus 0.000502. And again, that is what we get when we take care of that top term. Any questions so far on that? Okay. Then we're going to take care of the bottom term. So we'll swap out the orange maybe. And we're going to take care of this guy here. So again, we're going to, multiply in and multiply out. So I will put it right here. So if you multiply in, multiply out there on the bottom term, you end up with 0.000258 minus 0.00623x minus, right now the room will come underneath, 0.00414x plus an x squared. Again, same idea. We're going to combine the two x's there. These two guys will add, and rewriting it with the x squared first, x squared minus 0.0104x plus 0.40258. And again, that is the bottom term. Any questions on any of that math there? No? Okay. So now we got the top, we got the bottom. Now we need to multiply the bottom to the other side, but let me rewrite it on the next page here. So up on top, we had 4x squared plus 0.0896x plus 0.000502. On the bottom, we ended up with x squared minus 0.0104x plus 0.000258, and that equals our equilibrium constant of 54.3. Math-wise, we're now going to take our bottom term and multiply it over to our 54.3. That means up on top, nothing changes. Everything stays the same up on top. So we get 4x squared still up on top, which is now by itself, 0.0896x plus 0.000502. Again, taking the bottom term and multiplying it across to the other side gets us a 54.3x squared minus 0.5647x plus 0.001401. Now I take a nap and then I wake up and go, I need to combine everybody to the same side here, right? Personally, like I said before, I personally like to keep the x squared positive. You don't have to, but I like to do that. So because I'm going to do that, everybody on this side is going to be subtracted or moved over to the other side. When we finally do all that, we get our 51.3 x squared minus 0.6543x plus 0.000899 equals 0. And finally, we get our quadratic formula equation there that we could use. Any questions on any of that math there? All right. Feels like we should be done, but we're not. We can actually now do the quadratic formula, which is x is equal to r minus b plus or minus the square root b squared minus 4ac. That's going to be divided by 2a. Putting in our numbers here, that will essentially give us 0.6543 plus or minus the square root. If you clean up everything inside the square root, you end up with a number like 0.2436, which then needs to be square rooted to a number of 0.4936. And that's going to be divided by 2 times 51.3, which gives you 102.6. Doing the plus and then doing the minus of this, you get our two x values. We get an x value of 0.0112, or an x value of 0.00157. Any questions up to there? By the way, in case you're curious, I did it by hand myself. Yes. All right. So one of these answers will not make sense. In this case, they are both positive. So if we go back to our table, we do see that our values here that are minus x is 0.004 or 0.006, which means 0.01 is too large. If I point 0.01 into here, I am going to get a negative number. So in this particular case, this guy is too big. Again, going to give us that negative number when we put it back in. That means by default here, hopefully this should be our x value, which means we can now put it back in to our equilibrium line, and our equilibrium line for H2 is our initial, which is 0.00623, minus our x value, which is 0.00157, giving us an H2 concentration of 0.00466 molar. Our I2 concentration is our initial, which in this case was 0.00, and again, this is coming from the equilibrium line, 414, minus our x value of 0.00157, giving us for I2 a concentration of 0.00257 molar. And lastly, for our HI is our initial, which was 0.0224 plus 2 times our x, which would be 0.00157. And that gives us an HI concentration of 0.0255 molar. Those should be our equilibrium concentrations. A lot of math going on here, a lot of places where you could screw up. Might want to put it back in to double check. So if I take 0.0255 and square it, divided by 0.00466 and divided by 0.00257. I hope I didn't screw up. I end up with 54.3 basically as my K value, which is I think what we started with, right? So that is good. Any questions on any of those steps? Yeah. Yeah. Is it? Is it supposed to be 50.3? Yeah, that would be 50.3. That would be good. Thank you. That is 50.3. See, even I screwed up. So I didn't screw up too bad, I suppose, but that is going to screw up a few things, huh? So let me just double check that real quick. Yeah. Well, you know, it's close, I suppose, you know. That is 50.3. All right, so that is real quick, just see how bad I screwed that up. Hopefully not too bad. That minus 4 times A times C. So pretty close. So here, this will be inside the parentheses 2. This will be 0.247, for which if you take a square root, just to clean it up real quick, gives me 0.4972. And obviously that is 2 times 50.3, which is 100.6. There we go. So 0.6543 plus 0.4972 divided by 100.6 gives me an X value of 0.0114, which is still going to be too big, and 0.6543 minus 0.4972 divided by 100.6 gives me an X value of 0.00156. So not too much damage. So I imagine we'll end up fairly close to where we ended up there. 623 minus 0.00156 gives me 467 on this guy. And 0.00414 minus 0.00156, 258, which is probably why my K was very close. And 0.0224 plus 2 times 0.00156, or not that, 0.0224 plus 2 times 0.00156. 0.0255, so not too bad on that one there. So sorry about that. That should be a 6, and that obviously should be a 6 and a 6. So good way I don't round too much along the way. So very close there to where we got. You see, even I screwed up, to be honest with you. It happens occasionally. Yeah. Yep. Yeah, you really, you really should, yeah, do it. So it really is the right thing to do when you're doing a night table like this, when you are giving the initial concentration to everybody. So yeah, it probably would be part of maybe the point scheme of that, but just in general, you should do it. And obviously we couldn't do it on the previous one, right? Because we weren't given the concentration to everybody, but definitely when you do it, you should do it. A, to make sure you're not at equilibrium, which probably in most cases you won't be, because it wouldn't be much of a problem at that point. But, you know, just to make sure which way you should go. And like I said, even if you happen to blow by it, 9 times out of 10, you'll probably be okay if you assume it's going towards, you know, the product side, but you really should check. Other questions on that? All right, it's our day of ice tables. Yes, this is fun. Wow, not a lot of agreement there. All right, so let's do one more here to wrap it up for today. Let me rewrite the equations since things got moved. All right. The Kp in this case is 4.3 times 10 to the minus 4. We want to calculate the pressures of everybody at equilibrium. If you start with 0.862 atmospheres of N2, 0.373 atmospheres of H2 in a constant volume vessel at 200 degrees. By the way, temperature really has nothing to do with any of these calculations in most cases, if you're doing an ice table. So as I mentioned before, it works the exact same way as concentrations, except that obviously you're using pressure. So you just approach it the exact same way. So take a few minutes to see what you do, and we'll come up here together in a sec to the end just to kind of see, you know, if we're on the same page here. In this case, again, we have a Kp value, and we do have pressures given to us. And as I mentioned, you pretty much can approach it the same way. We could write our Kp expression in this case, which would be the partial pressure squared of NH3 divided by the partial pressure of N2 times the partial pressure there cubed of H2. And again, this would equal 4.31 times 10 to the minus 4. In this case, we will start with our ice table like normal here. So we have N2H2. There and a 3 there. And initially, as we can see, we've got 0.862 and 373 on the other one. So initially 0.862, 0.393, was it? 373, thank you. And that would be 0. Our change would be minus x minus 3x, right? Because of the coefficient, we still need to do that. And on our product side here, it would be 2x. As again, we could safely assume that it is going to the product side since we aren't given anything about the products. Equilibrium here, 0.862 minus x, 0.373 minus 3x, and a 2x. This again will go into our Kp expression. And our Kp there again would be our products, which would be 2x squared divided by 0.862 minus x and 0.373 minus 3x, which we do need a cube as well. And that equals our, what we got there, 4.21 to the, what was the case? To the minus 4, thank you. That first numbers are correct, right? Yep. All right. So at this point, there's a lot of math going on here. We got some cubes. We got some squares. 4.31. All right. It's the end of the week. I'm old. That's what it happens. Hopefully, I'll find my car later. It'll be okay. All right. So in this case, that's a lot of math that we don't really want to do. So clearly, we should just go to the next problem. And it seems like the right answer there. But we could try to find perhaps a better way of solving this than doing the math. Let us look at the hopefully correctly written there Kp value. This value right here, is that a large value or a small value? That is a small value of K, right? Which means when we reach equilibrium, we should mainly have reactants or products. We should mainly have reactants, right? So small value of K means that we should mainly have reactants at that point. That means if we mainly have reactants, the change part here is going to be a lot of change or not a lot of change happening. Not really a lot of change is going to happen because of that. So in these situations where you have a relatively small K value, you can make an assumption and assume that X is equal to 0. Now, clearly, you cannot kill all the x's, otherwise you have nothing to solve for. So the x's that we're talking about are any x's that you're going to subtract from a number, or like in the previous one, any x's you would be adding to a number. So what that means, it's really this x here where we're going to subtract, this x here where we're going to subtract, and obviously we need to leave the x there on top. And if we do that, that makes this a little bit, hopefully more manageable. That gives us 4x squared up on top, gives us 0.862 on the bottom times 0.373, and we still need to cube it. And that does equal 4.31 times 10 to the minus 4. Much rather solve that one than the previous one in terms of the math. So what we're going to do is clean up the bottom on the left. So we're going to take 0.373 and cube it. We're going to times it by 0.862. And basically that gives you a number like 0.0447, which we're then going to multiply to the other side. And we're going to multiply it by 4.31 to the negative 4. And that is going to get us 4x squared is equal to, I believe, 0.00000. That's a lot of zeros there. 4 zeros. There we go. 1928. At this point, we're going to divide by 4 and also take the square root of it. And if we do both of those things, we're going to divide by 4 and also take the square root. That is going to give us an x value of 0.00220 in this case. Any questions so far? Now, there is a rule that if you do this assumption, you do have to check your assumption to make sure it's okay. And there's a couple different ways to check your assumption, but in our class, we will use what is commonly referred to as the 5% rule. And the 5% rule means that you basically take the x value you just got, which was 0.00220, and you divide it by the number you're going to subtract it from. So we would divide it by 0.862 times it by 100. The good news here is if we are less than 5%, you're golden. Yeah, so in this particular case, you're at 0.25%, which means a very happy face. We are good to use that as our x value. You could also check the other one. You just take 3 times your x value and then divide it by 0.373, times it by 100, and you'll still be under, I think it's like 1% or something like that on that particular one. Usually, if you check one of them and it's good, it's usually pretty much good for everybody. But if you want, you can check them both. And again, if you're going to check the other guy, you basically would take 3 times 0.00220 divided by 0.373 and times 100%. And I believe you're good as well, you know, in that. You would not have to cube it. You just actually put it into the equilibrium here. You put it in there, yeah. All right, so because we're good, we actually could finish our answer here. This is an appropriate x value to use. It would go back into our table there and go back maybe this page here. So in our table, we had 0.862 minus x, which in this case was 0.00220, and that gives us 0.862 minus 0.00220, gives us a we'll call it 860 atmospheres for our, that was N2. For our H2, it was 0.373 minus 3 times our x value, which is 0.00220, and that gives us 0.37 minus 3 times 0.00220. Gives us a pressure for this guy of 0.366 atmospheres, and lastly for this guy at equilibrium was 2x, if I'm not mistaken. And that should then be 2 times 0.00220, and gets us a 0.004 atmospheres for our NH3. Question on that there. Makes sense based on our K value was a small value, mainly reactant, so most of it comes from the reactant side. Not a lot of pressure happening on our product side in this particular case because we're not making a lot of products, so not a lot of gas molecules there on the product side, so not causing a lot of pressure on the product side. Question on this type of ice table. In our big day of ice tables today, we've now done 3 different ways to solve ice tables. You could have a perfect square, quadratic formula, and you can make an assumption. Again, only if the K value is small, you can make the assumption. That is also why we did not do it on any of the previous problems, because the K value was 7 and 54.3, which is a large value of K, so you cannot do the assumption. Any questions on any of that there?